Okay, let's start our second panel. I think I was introduced earlier, but I'll just say my name again. I'm Mary Anderson. I'm Emeritus Professor from the University of Wisconsin-Madison, and very pleased to be moderating the second part of the panel discussion. We have three speakers, and they'll come up in order as on your schedule. Our first speaker is Jay Famiglietti. He's a professor of Earth System Science at the University of California in Irvine, and he's currently transitioning to NASA Jet Propulsion Laboratory, where he's worked several years now as a senior water scientist. The NASA Jet Propulsion Laboratory is at the California Institute of Technology. Dr. Famiglietti is also the founding director of the Center of Hydrologic Modeling at UC Irvine. He served as the founding director. He's a member of the California Water Board and has been quite active in advising California on its various water problems. He's very well known for his work on remote sensing of groundwater depletion, and he and his research group use satellites and advanced computer models to track freshwater availability. He's a fellow of the American Geophysical Union and the Geological Society of America. He's a regular advisor to the Congress and the California Governor's Office, and he's participated in numerous discussions at the federal level, including with the White House. So without further ado, let me just turn this over to Dr. Famiglietti. Jay.
Thanks very much, Mary. So first I wanted to say to Stavros, don't worry so much about what you say to students, because sometimes, there's a positive effect. And so although George Pinder wasn't my professor, I took my groundwater modeling class with George. And we had an oral exam for a comprehensive exam. We had an oral exam, and I walked in. So I had taken his modeling class, and so then you go and you kind of talk over the questions that might be asked on your comprehensive exam. I walked in, and he didn't really know me that well. I said, Dr. Pinder, I work for Eric Wood, and I do surface water. And he looks at me, and he says, surface water? It's groundwater, man. It's groundwater. So all these years later, I have been spending a lot of time on groundwater, although I really am a surface water modeler. So I want to talk to you about some of the work that we've been doing with GRACE, the Gravity Recovery and Climate Experiment. And thankfully, it's come up a couple of times. And Bridget explained it a little bit. But, in a sense, the bad news tour is going to continue. So I found, I really enjoyed the earlier presentations. There's a part of them that are a little bit depressing in terms of the massive amounts of groundwater depletion that we're seeing all over the world. And here's some examples from California and from the Middle East and from India. So GRACE stands for Gravity Recovery and Climate Experiment. And I like to say that it works like a scale in the sky. And speaking of size scale, you can see how big the satellites are over on the right. Really, if you just put about two of these round tables together, they're about that big. So I like to say that it works like a scale in the sky for the following reason. The two satellites orbit at about 400 kilometers, and they're separated at about 200 kilometers. So pretend these are the satellites, and they orbit over the poles in near polar orbit. As the satellites encounter a region that's gained water weight. So say some of the flooding that we've been having in this region because of the hurricane, that region has gained water weight. And when the satellites fly over the region, that region exerts just a slightly greater gravitational tug on the two satellites and pulls them down. Okay? And what's very accurately recorded is the position of the satellites. George, you missed my George Pinder story. I'll tell you later. Okay, so they get pulled down when they're in regions of water weight gain, and likewise if they're flying over California during the drought, that region has lost water weight and it exerts slightly less of a gravitational tug on the satellites. and they fly a little bit higher in their orbit. So by keeping track of the ups and downs and the intersatellite distance, we're able to map out over large regions the areas of the Earth that are gaining or losing water mass on a monthly basis. So we're looking at the delta. We're looking at monthly and longer time scales. We're looking over large areas like 150,000 square kilometers or bigger. So it's really good to put things in a regional and global perspective. We have a relative error of about 1.5 centimeters of water thickness on the surface. And it tells us not how much groundwater there is or the change in the groundwater, but the change in the total amount of water stored. All of the soil, moisture, surface water, snow, and groundwater together. So we have to do some work with other data sets and other satellites to pull out just what's happening with the groundwater. So that's where a lot of the research comes in. So that's GRACE. It launched in 2002. I didn't know it was St. Patrick's Day. It's because I'm not Irish. Now I know. And it was designed to be a 5-year mission. And it's nearly dead. Batteries are dying. We're collecting about 9 months of data per year out of 12 now. But help is on the way, and that's called the GRACE follow-on. It's almost exactly the same mission with exactly the same specifications, or pretty close. So, and this will launch at the end of 2017. I heard it might be pushed into 2018. So we're hoping that the current mission overlaps a little bit with the new mission, and we have continuous data. Okay, so what does some of the data look like? Here we are in California. We're looking at the combined Sacramento, San Joaquin, Tulare Lake basins, and that blue part there is the Central Valley. So what are we looking at here? These are time series. This is a time series of GRACE data for the change in the total water storage for that region outlined, the greater red region, the Sacramento, San Joaquin River Basin. So we're looking at wet season, dry season, and they're monthly data. So wet season is the winter, dry season, we go through the growing season, and then we bottom out in November. Wet season, dry season. So we're looking at the change in water storage, the weight gain, the water weight gain, the water weight loss on a monthly basis, going back to 2002. This one stops in about 2015. So that in itself is an engineering marvel to be able to have a time series of data that shows holistically all the water that's available in California on a monthly basis. Is quite an achievement. It's something that is very, very difficult to do when we just use ground data alone, right? So it's extremely complementary. You know, one of our big goals is to integrate all these things. Yeah, we're going to use the cloud, but to integrate all the data into models, the ground-based and the remote sensing data into models. So what sort of information here are we getting? Well, we can start to look at, say, the growth of the drought across the West, and we can start to look at some of the time scales of drought. So this is our current drought, nominally started in 2011. And so we can now quantitatively say, hey, you know, California is losing about 15 cubic kilometers of water per year, which is a lot because all 8 million Californians, 39, it's probably growing by the time I finish my talk, use about 10 cubic kilometers of water per year. So we're losing more, right, than the population needs, and about 2/3 of that, turns out from our research, is from groundwater losses. So we can start to quantify those things. We can say, hey, you know, maybe this drought has been going on a little longer than, right, just since 2011. Maybe this was a little bit of an anomaly here, and it was sort of a mini El Nino. But really, when we look at this figure, we see that California, the whole time we've been looking using GRACE data, this particular region has been losing water the whole time, okay? And we can quantify the rates. And one of the big reasons is because of groundwater, okay, and depletion of groundwater. And this is a chart that combines the USGS data from the Central Valley hydrology model, shown in red, and the GRACE data in green. Now we're just looking at groundwater, going back to 1962. So we see this long-term depletion The colors in the background represent whether it's a wet period, really wet, like in the darker blue, really dry, like in the darker tan, or moderately wet, moderately dry in the in-between colors. And so we see the long-term depletion. And we see that there's a little recovery in wet periods, but a big decline in dry periods, right? As you've heard, right? Farmers use a lot of groundwater to grow food, have to rely more heavily on groundwater during drought. So we have these big drops. We have a Sustainable Groundwater Management Act, right? So maybe the goal here is to change the trend. Maybe you want to raise the trend a little bit. Maybe you want to flatten it out. You have to figure out how to do that. But like Jim was saying, for the most part, this water's not coming back. And one of the things that might have been missing in the last panel was that there are lots of engineering methods to help us manage what we have, but we're not really bringing that water back. Okay, it's for the most part gone. So we're not engineering our way out. We're not going to engineer our way out of the problem. We're not going to eliminate the problem, but we can manage the problem. So here's a trend map. Another way we look at the data is to map out the trends. Okay, so now we're looking at the whole United States, and for most of the grace time period, and the blue is getting wetter, and the red is getting drier. So we see a couple of things. Upper half of the United States is getting wetter. The lower half is getting drier. And here's our two big aquifers, southern Ogallala and the Central Valley. And clearly we're using more water than we have available to us. And these are showing up as hotspots on this map. This map points, I think, to bigger problems that are national scale problems. One of the problems we face in California and probably in the southern high plains as well, because we grow so much food, there's chronic water scarcity. The drought, comes and goes, but we're continuously running out of water, okay, in those regions, as you saw from that long-term combined USGS GRACE plot. So we have to figure out, as Jim said, how are we going to grow food with less water, basically, right? As well as, face the future of the haves and the have-nots, right? The upper half is getting wetter, the lower half is getting drier, the water table in California is falling, wells are going dry, streams are being depleted, all the things that you heard about or will hear about the subsidence in the next presentation. So we're past any safe yield sustainability, certainly in California. But still, we need to affect some kind of change. So now we're going to make matters worse, and we're going to take that map and look globally. And so same color scheme. And now we've labeled the major trends, and the biggest losers are the Greenland and Antarctic ice sheets. And after that, the Alaskan glaciers and the Patagonia glaciers. Just about all the other red spots are related to major aquifers around the world. And so someone asked the question about how many of the aquifers, over half of the aquifers are being depleted. So a lot of those red spots are places that are aquifers, and we know they're aquifers. And so when you see them in this context, sometimes when we look at the aquifer scale, the numbers get smoothed out a little bit because the aquifers are bigger than these hotspots. The hotspots are a little smaller, so there's more intensity when you look at the map this way, the intensity of the rates of depletion. By the way, of course, implications for conflict in the Middle East and India, Pakistan, and Bangladesh, and all that, right? We appreciate it, and I've shared this data with the State Department and so on. So we know those hotspots are related to aquifers because here's the map of the aquifers. So we just took this trend map and mapped the rates for to the template for the aquifers. And so the question came up before, how many aquifers are being depleted? This one shows that over half of the world's 37 largest aquifers are being depleted or past sustainability tipping points. The outflows are greater than the inflows. So this is problematic. There's a climate change part to it as well. Same map. This is that same trend map, just a slightly earlier version. And you know, the IPCC models suggest, the climate change models suggest that the wet areas of the world are getting wetter and the dry areas, or will get wetter, and the dry areas of the world will get drier. And so for a long time, I've been looking at this map and in these presentations saying, see, I think this is happening. And, you know, ask the question. And here's what I mean about the IPCC. This is a famous figure about how precipitation may change, multi-model prediction of how precipitation rates may change by the end of the century. And so I think we're already seeing it in the GRACE data. Is it climate change? You know, I don't know, but the pattern is that pattern. And this is a paper that came out earlier this year. So we just took all the wet areas and looked at the trend, and all the dry areas and looked at the trend, and that's that negative trend. And this is actually a sea level paper. We were talking about sea level rates of sea level rise before. So we're looking at the total land contribution. When you add up all of the land areas, what's the contribution to sea level rise? So, you know, there's a climate change part to it too, and so there's a global groundwater crisis. This is a paper that I wrote in 2014, and maybe some of the things we will talk about in the panel discussion, but just to sort of summarize what I've talked about. You know, we face chronic water scarcity in some of these food-producing regions, in many of those regions, and that's why the aquifers are being depleted. So we have to figure something out. And we need to deal with the fact that population is growing and food production. So an important message, you know, subtext of everything that all of us have been talking about this morning is that food security is at far greater risk than people realize. And that's because much of the food production is irrigated using groundwater, and the groundwater is disappearing. Okay, so new paradigms in agriculture. I mean, Jim was talking about what needs to be done. You know, do we need a national policy or a strategy or at least a plan? And the reason I say that is because when you go back and look at that national map, that's a national problem, or at least it's a bunch of regional problems, right? And the food that we eat that's grown over the Ogallala Aquifer and grown in the Central Valley, this is a national problem. We eat it, we're going to eat some of it for lunch, okay? But we're trying to do just from water that's in those particular regions. So we need to be thinking more broadly. Governance, policy, water rights issues, right? We could go down the rabbit hole with that one. And I mentioned this, the social inequities, the haves and the have-nots, and the potential for conflict. I think this is my last slide. And so one of the things I want us on the modeling side to do, and we're doing it in some sense, is to build models that can integrate all this information and then predict, or at least become a playground to test out different adaptation strategies. This is just a simple model. It's like a regression model of California water, California groundwater. On the left, we've got the USGS in the dots. It's the USGS and GRACE data, that same plot I showed you before of the long-term decline. And then the simple empirical model that we built that matches it pretty well. That's the solid line. So we've got observations and model. And then on the right, just playing with, what happens if we do nothing? Well, okay, that's not good. And what happens if we reduce, 20% reduction in agricultural use? What happens if we do 20% in agricultural use and add in some efficiencies like recycling or conjunctive surface water management or whatever? So this is the sort of stuff that we need. I mean, this is a very simple model. We need to be, the kind of models that we were talking about here today. This is what we need to be doing with those models. This one is too simple. It's more for demonstration. I think that could be it. Yeah, that's it.
Thank you, Jay. Well, we have some time for questions, and could I please ask the speakers to clearly identify yourself for the record, because we are recording this. Do we have a microphone here for the speaker? Okay.
Oh, thank you. You said that if there was a 20%...
So, Charles, could you just...
I'm sorry, Charles Fairhurst from NAE, Section 11. You said if there was a reduction of 20% in the agricultural use of water, right, that things would be much better. What is the potential to increase the production of food with 20% less water?
Excellent question. And the slide was meant to, was more or less for demonstration purposes only. And so, we're not ready to say if we reduce by 20%, we're going to get this sort of change. What I really wanted to demonstrate was we're building a tool where we're turning knobs and trying to get more realistic, more responses in which we have more confidence. But the question you asked was, if you reduced agricultural water use by 20%, could you still have the same productivity? I have no idea, but my guess is yes. But that's easy for me to guess, not being an ag guy. What do you think, Jim?
But could I
think it's real possible.
Yeah. What I was going to ask was that currently the increase in food production has been by the use of fertilizers, etc., which have a side effect of contaminating the water that runs off.
Yeah.
And I'm just wondering what is the real potential?
Right. So good question. And we would love to build the super model that can do it all. And I will probably never get there in our lifetimes.
Kirk Hatfield, University of Florida. Well, there's two aspects of this. One is you could use the GRACE data for Kansas to look at, I suspect, the approach that Jim produced earlier, which might be kind of interesting to see what better performance you might see with all this data gathered over such a large scale, and with the fact that you got so much in the way of actually pumping usage data. The other aspect of this problem that I think we don't want to forget is that we waste about somewhere between 40 and 60% of the food gets wasted before it even leaves the field. Wow. So you imagine the water savings that could be achieved if we could overcome that issue alone.
Right.
Any other question? One, okay, right here, right up here.
Yeah, so from Columbia University, NAE.
Could we get the name better? I didn't.
Som Samasandran from Columbia University, NAE Section 11. Okay. The decreased water availability doesn't necessarily have to lead to decreased food availability. Engineered solutions such as microparticles that can absorb water when it rains and release water when the tree and bushes needs can really lead to. Another area that can lead to increased efficiency is there's so much water wasted from dams to farms through viaducts. In India, for example, there's so much cracks and 40% of the water is wasted. It is possible to seal those areas and decrease the waste.
Yeah.
So
infrastructure improvements are, my gosh, I mean, in cities, I guess it depends on the city. The city where I live, we probably have we probably lose about 50% of the water. But no, you're absolutely right. So improving transport and leaks and all that stuff, I mean, it's probably on the 20 to 30% level, right? Without even touching water use on the farms.
Okay, last question.
Mahta Mogadam, University of Southern California. Jay, my question is, what is your estimate of partitioning of water content in the soil versus aquifers?
Yeah, so it varies, right? I mean, it varies quite a lot, and it just depends on where you are and the depth of soil and so on, right? And so we look at all of the trade-off of all of those. So the question, I think, was basically, how much soil moisture is there versus groundwater versus snow and surface water. And so it changes. I mean, it just changes all over the place, right? So there's no one answer. But that's one of the driving forces for the work that we're doing on the modeling side to integrate the data to integrate not only GRACE, but the soil moisture satellite called SMAP, the future SWAT. Someone was asking about other missions before the SWAT mission, which is SMAP is soil moisture, active passive soil moisture mapping. SWAT is surface water and ocean topography. We'll be mapping starting in 2020, the distribution of water over the surface and the GRACE data. And so ingest those all into models at different scales to get a better understanding of exactly that question. A lot of which, sometimes if we don't have the data like they do in Kansas, sometimes hard to know.